Everybody. So today I'm going to start a new chapter, that is electromagnetic induction. So to start this chapter, let me recall. Maybe a long back, we have two different branch of physics, that is electricity and magnetisms. And when we discuss chapter number 4, I've given you a understanding that current carrying conductor gives magnetic field. It was Orst, right? Hence Christian Orst, who found that current carrying conductor produce a magnetic field. So I told you that day that this understanding or this discovery brings some kind of a relationship between this current and or electricities and magnetisms. All right. So the point is, if the current carrying conductor, if a current or moving charge produce a magnetic field, then the point is the converse effect possible? The question arises is that if the moving charge produce a magnetic field, is the converse effect possible? This is the one question, right? That arises in many arose in many physicists, right? And then another question that can be asked is, can moving magnet produce electric currents? All right, or we believe that normally in nature the events or the phenomenon looks very symmetry, right? The nature is very symmetry. If I say if a nature is very symmetry, if moving charge produce a magnetic field, and why not moving magnet produce electric current in a coil or in a circuit, right? So another third question is, does the nature permit such a relation between electricity and the magnetisms? That what is that such a relation? Such a relation is that the moving charge produce a magnetic field that was discovered already, and then the moving magnet can produce a magnetic field, can produce an electric current. So this and all these questions, right? This is some kind of challenge, right? So this challenge was taken by these two physicists, right? That is Michael Faraday and Joseph Henry, right? And they boldly took this challenge and then say that this nature is a symmetry, so nature looks very symmetry. So therefore, moving magnet can produce electric current in a circuit. All right. So in 1831, these two scientists separately, one in the United States, another in England, they perform an experiment, a simple experiment, and could discover that moving magnet produce electric currents. All right. So when the work of the Michael Faraday was first published, right, and he could able to produce a very small current, that means milliamperes, right? The moving, if I move a current, if I move a magnets, and we could able to produce a very small current in a wires. So the critics, right, says that what is the use of that small current? And then his answer was like, what is he just asked the right answer, like in a question form, right? That is, what is the use of small a newborn baby? And that's the newborn baby. We have to nurture and then become big, right? Likewise, his concept, right? His understanding about moving the electromagnetism or the electromagnetic inductions, the latter, right, was foundation for entire electricities. All right. So in this chapter, what we are going to study is electromagnetic inductions, how changing magnet or moving magnet or changing magnetic field produce current in a coil or in a circuit. That's the entire that is the point that we are going to discuss in this chapter, right? So therefore, that new discovery, right, the moving charge produce magnetic fields is the foundation for entire electricity, right? The electricity that we generate these days is outcome of these two or scientists, right? So this is all about introduction, right? So now next I would like to do is the basic, most fundamental concept about electromagnetic induction, that is these three experiments done by two scientists, right? So the experiment of Faraday and Henry, right? This is very simple, maybe I taught in our class 10 also, right? So what happened is, the first experiment is that this is a coil, and I put a galvanometers. The purpose of putting galvanometer is to see whether current is induced or not, right? Then what I'm going to do is I just move a magnet towards the coil. This coil number 1, that is C1 is coil number 1. If I let a magnet to move along this coil, what we found is the galvanometer shows a deflection. Why we use galvanometer? The galvanometer is very sensitive. So therefore, even a microampere can be detected by galvanometer, right? So this is the point. So when I move a magnet closer to this, that means magnetic field is increasing. Magnetic field is increasing, thus the magnetic flux is changing. And the magnetic flux across this coil is changing with times, thus current is induced or EMF is induced. EMF is induced or current is, right? EMF is induced, thus current is induced. Thus current is. This is the first experiment. And then if I move a magnet in opposite directions, alright, there will be a induced current, but the direction of current is opposite. This was found by these two scientists. Alright. And then one more point is, if I move faster, then there will be a greater induced current. The current induced is going to be greater if I move faster. Why? If I move faster, the rate of change of magnetic field or rate of change of magnetic flux is going to be greater, and thus the current is going to become more. So this is one point, right? And then if I reverse, instead of north and south, if I say south and north, these directions, and there will be a current, but direction of current is opposite to that. Why? Because now the south is facing toward the coil, and then there is a change of magnetic flux. Alright, so thus the direction of current is going to change, right? So this is the point. If I move in opposite directions, direction of current is going to change. Why? Because it is a decreasing magnetic flux. And if I change the pole of a magnet, again direction of current is going to change. Why? Because magnetic field is going to reverse. If I reverse the magnetic field, then the induced current direction is going to change. If I reverse the direction of motions, then EMF, the direction of current is also going to reverse. Why? Because this is increasing. If I move in opposite direction, this is going to become decreasing. So this is the point. This is the first experiment done by two scientists, and the second activity or second experiment was this. So now instead of bringing a coil, instead of bringing a bar magnet, I can bring a coil with current. So we say that this is going to be a solenoid which produces a magnetic field, right? The same experiment actually, right? So if I bring it closer, there will be a current in a coil, and because of which they produce a magnetic fields, and then if I bring it closer, magnetic field across this is going to change, greater and greater magnetic fields, because of which there is induced EMF and induced current. Alright. If I bring this in opposite directions, there will be a change of magnetic flux across this coil, and however the change is in opposite, therefore direction of current is going to become a reverse. Direction of current is going to reverse. So that's the simple, right? Now again, I will say if I reverse the direction of current here, Alright, here instead of current like this, if I say current like this, then if I move in that directions, the direction of current is going to reverse. Why? Because if I reverse the direction of current, then the direction of magnetic field is going to reverse. How are you going to reverse the direction of magnetic field in a solenoid? Just reverse the direction of a current. If I reverse the direction of current, then the magnetic field produced by a solenoid or coil is going to change. So this is second experiment. The third experiment is that I have a two coil, alright, I have a two coil, and then one coil having a battery or cell connected, and other coil we have a galvanometer. So if I instead of moving, I just switch on, or if I close the circuit, immediately there will be a magnetic field, right? So you will see a momentary current. There will be a current for a very short period of time, then it stops. That means there is a change. Change is instantaneous. This change is instantaneous, right? So as soon as I close the circuits, there will be a magnetic field, and then this produces a magnetic field. This produces a current, but no steady current. There won't be any steady current. Why? Just momentary current, right? So this is the point. Now the point here is, if I instead of moving, if I keep this at rest, if this is at rest, then there won't be any induced currents. There won't be any induced current. If this is at rest, then there won't be any induced current. There won't be any induced EMF, right? Again, if I say if it is at rest, there won't be. It has to move, right? If it is at rest, then magnetic field doesn't change across this. Therefore, no magnetic flux is going to change. Therefore, there won't be any induced EMF. So this is the point. So therefore, the moving magnet produce electricity, or moving magnet produce. Why moving magnet produce electricity? Moving magnets give rise as changing magnetic flux. Alright, so this is the concept. Alright, so now before I start, the most important topic of this term, that is the Friday law of magnetic inductions. First, let me have the brief idea about what is magnetic flux. This is a very important concept. Alright, very similar. The concepts are similar whether I say the electric flux or magnetic flux, right? So when I say a magnetic flux, alright, so this is a flux. This is a small flux, right, for a small area, right? So this is the flux. I'll just say before I say this is the flux B area, right? So magnetic field along this, shall I say I put A, I'll put A, right, instead of S. This is the magnetic field along this area. This tells that magnetic field along area A. Alright, magnetic field along area A. So BA cos theta, where theta is angle between B and area. This is the point. If I say if a theta is 0 degree, then flux would be a maximum. If theta is equal to 90 degree, then there is no magnetic field along area, that is going to be 0. That's the point. Okay, that is to keep in mind. This is very important concept, right? This is a flux. For a small area, the flux is going to be delta area, right? Delta A, shall I put A? Alright? So if I sum up This is magnetic flux. So theta is angle between magnetic field and area. So if I let me give you one example, right? If I have magnetic field in these directions, this is the magnetic field directions, and I say I put area in this direction, I put area in these directions, and then direction of area is this, and direction of magnetic field is this. So there's no magnetic flux passing through this. There's no magnetic field passing through this area, right? So the flux is going to become zero, right? Flux is going to become zero. No magnetic field passing through this area, all right? Another example I would like to give you is, this is magnetic field, and this is area, and the direction of area is n cap. This is magnetic fields. Magnetic flux would be equal to VA. This is the maximum. Why? Because entire magnetic field pass through this area. That means magnetic field is along a direction of area. Magnetic field is along a direction of area. So this is what we have in case of flux. This is what we talk about magnetic flux. Okay. Now, having this concept, I would like to do a very important topic of this chapter, that is electromagnetic inductions. So Friday law of electromagnetic inductions. Alright, so this is what we have, right? Now instead of saying like rate of change of magnetic field or rate of change of, what I would like to suggest is rate of change of magnetic flux, right? So this law, the Friday law of induction, says that the rate of change of magnetic flux, right? The magnitude of induced EMF, right? Magnitude of induced EMF in a circuit is equal to the time, the rate of change of magnetic flux through it. So that's the point. So I say this is EMF induced. This is EMF induced. EMF induced is magnitude is going to be this. This is what we have. This is what we call law of induction. If a flux is changing, then only then there will be EMF. So the EMF is going to be greater if a flux is going to be greater. If rate of change of flux is greater, EMF is going to be, I say, if EMF is going to become zero, if a flux is constant, if a flux is constant, EMF is going to become zero if a flux is constant. Flux is constant. So if a flux is changing with time, only then there will be a induced EMF. Alright? There will be induced EMF. Right? So this is, I say, this is a flux across each turn. I can have n number of turns. I can have n number of turns, right? For n number of turns, I can say this is for 1 turns. This is for n turns. This is very, very important. So, induced EMF can be increased by increasing number of turns. This implies that induced EMF can be increased by increasing turns, increasing number of turns. So therefore, we prefer having so many turns of wires, right? That's one very, very important. Now the point you will ask is, what is the minus? What is the significance of minus? So the Faraday law doesn't talk about minus. However, this minus is very important. The significance of this minus tells you the polarity or a direction of EMF. Oh, this minus tells about direction of currents. This minus tells us about the direction of current. So this is the direction of current, right? So I say if EMF is induced, where would be a positive potential, where would be a negative potential? That is, we talk about polarity. So that answer, that question, that answer is given by minus signs. All right. So the significance of minus sign tells the direction of currents, or it tells the polarity of EMF or direction of EMF. This is very, very important, right? So now the minus signs, the significance of minus was answered by another scientist. We call it as a lens, and then it was done under a law called Lenz's law. Okay, so this was done, right? So let me write down law, electromagnetic law of induction, Friday law of inductions. So this EMF is equal to minus n d phi naught d by dt, and this is the very important one. All right. So it was Heinrich Lenz who answered this, right? That is why there must be a minus, right? This is very, very important, right? So this is he answered this under a particular law for Lenz's law, and then his law, or his explanations and his understanding about the Lenz's this minus is consistent with conservation of energies. So therefore, this law is true beyond the doubt, right? So therefore, everything has to obey law of conservation of energy. So therefore, the significance of minus is that significance of minus tells you the direction of currents. And how you found the direction of currents? The direction of current is found by Lenz's laws, and that direction is very much consistent with law of conservation of energy. All right. So it was found by Heinrich Friedrich Lenz, right? So I would like to give you what do you mean by Lenz's law, right? So the Lenz's law says that yes, if I change the direction, or if I change the magnetic flux across any coils, and there will be a EMF induced, and hence there will be a current induced, and his understanding was that the EMF or the magnetic field produced by induced EMF or induced current is such that this opposes the changing magnetic flux. If I say if a magnetic flux across a coil is increasing, let's say magnetic flux across a coil, let's say this is a coil, right? Magnetic flux across this coil is increasing, then there will be a current, there will be induced currents in a coil that opposes the change. That induced current is such that the magnetic field produced by induced current opposes the change. What is the change? Change is increasing. That means opposes the induced current try to decrease the increasing current. Induced current try to decrease the increasing current. Let's say if this coil is subjected decreasing magnetic flux. Let's say magnetic flux across the coil is decreasing. Then there will be an induced current, no doubt. There will be an induced current in a coil. Such that in magnetic field due to an induced currents increase the decreasing magnetic flux. Increase the decreasing magnetic flux. Alright, why? Because this coil experiences a decreasing magnetic flux. So what current does is the induced current try to increase the decreasing magnetic flux. That means it opposes. It opposes the change. That means in a very short sentence, I can say the direction of induced current is such that it opposes the change of magnetic flux. It opposes the change of magnetic flux across coils. Alright, so this is the point, right? This is his understanding, right? So therefore, let's say the law, it says that the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produce it. Alright? Which opposes the change in magnetic flux that produce it. Alright? So this, now I'll give you, don't worry, right? I'll explain you, right? With greater detail, right? So this is what I have. Now this magnet is approaching. This magnet is approaching, and the coil experience. This coil will experience increasing magnetic flux. Increasing magnetic flux. Magnetic flux. All right. Now, current in a coil, the direction of current in a coil such that the magnetic field due to current, induced current opposes the change, right? I say direction of currents is such that magnetic field due to induced current, I just say induced current opposes the increasing magnetic flux. Increasing magnetic flux. Direction of current is such that magnetic field due to induced current opposes the increasing magnetic flux. So how to oppose the increasing magnetic flux? Alright, I have to put this in this term. This is magnetic field due to induced current. This is the magnetic field, right? So by this you can decrease the magnetic flux. Right? So however you get it. So if a magnetic field goes in these directions, then induced current is this. The right hand thumb rule. So you see this is the direction of current. This is the direction of current. Alright. This current could produce these magnetic fields. This current could produce this magnetic field. This magnetic field opposes the increasing magnetic flux, increasing magnetic field or increasing magnetic flux. Alright, so this is the point. Now next here, now this is receiving, it's going away. Now this experience decreasing magnetic flux. Now this is second point, decreasing magnetic flux. Decreasing magnetic flux. Now if it is decreasing, then induced current, direction of current is such that magnetic field due to induced current increases decreasing magnetic flux. So direction of current is such that magnetic field due to induced current increases the decreasing magnetic flux. How to how to increase the decreasing magnetic flux, then direction of current should make this is a magnetic field directions, right? And such a magnetic field is current direction of current must be like this. Direction of current must be like this. Okay, so this is how it goes. This is how it goes. Now look at here. The picture it says that, and this says that this again this tells you the direction of this tells you the direction of current, right? So this is how it shows your directions. It goes like this. So that means this is the north face, right? If I have a coil like this, this face is a north. Why? Because the letter also resembles north. And this is the direction of current, and the coil that is facing towards this receding or north pole is the south pole, and this is the north pole, and this north pole, this is the south pole, north pole. So I say there will be repulsions. There will be repulsions. For this there will be attraction, and then I will explain you this, right, again. Alright, this is the point. Okay, now I'll explain you again. Now let's say if I have a south pole. Now if you don't understand properly, again I'll give you one, right? So this is the coil. This is the coil, and this is the south pole. That south pole means direction of magnetic field is this. Alright. So this experiences the increasing magnetic flux. Alright. So if this experiences the increasing magnetic flux, then magnetic field is going to be along this. Magnetic field is going to be along this. Magnetic field is going to be around this. This is induced magnetic field. This is induced magnetic fields. This is induced magnetic field. And what about the direction of current, right? The direction of current will be this, right? Alright. So therefore I just say, instead of like this is the direction of current, right? Here. This is direction of current. And this looks letter S. This look letter S. The letter S. So therefore, south pole is facing towards south. So I'll be having a ring. All right. The face, this face appears south, and other face appears north. Right. So therefore, this is going to be repulsion. Right. There will be repulsions. There will be repulsions. Likewise. South going away, again magnetic field is B, and I'll be having coil like this. So now this is decreasing, right? Now decreasing magnetic flux, so I have to increase the decreasing magnetic flux. I have to increase the decreasing magnetic flux. So this is going to be induced magnetic field, and this is going to be a current. This is going to be a direction of current, and this current will give you this magnetic field. So therefore, this is going to be a direction of current. So therefore, the south is facing toward the north. So instead of repulsion, you have attractions. This is what we have. What I call attractions. This is what I call attractions. So that means if you try to take magnet away from coil, there will be attractions. If you try to pull a magnet towards the face, there will be a repulsion. So I will tell you the significance of this. Alright. So this is what we call as a Lenz's law. So now we could able to predict, or we could able to tell the direction of induced current, right? And magnetic field, polarity of EMF. So this is what we have, right? So very simple, right? If I say if it is falling, right? If it is at rest, no motion. If it is at rest, then coil doesn't experience any change of magnetic flux. If a coil doesn't experience any change of magnetic flux, there won't be any induced current, right? Now this is falling. If this is falling, there is an increasing magnetic flux. If there is an increasing magnetic flux, then a magnetic field produced by this coil try to decrease the increasing magnetic flux. Magnetic field produced by this coil try to decrease the magnetic flux. So therefore, this is going to be magnetic field due to induced EMF. This is alright. So such a magnetic field is given by this current, right? Alright. So B is increasing in the loop. If a B is increasing in the loops, the magnetic field produced by a loop is trying to decrease the increasing magnetic flux. Alright. If B is increasing in the loop, then magnetic field produced by a loop tries to decrease the increasing magnetic flux. So this is the point, right? So now if it is going up, this loop experiences a decreasing magnetic flux. If this loop tries to decrease the magnetic flux, so if this magnet is going away, going upward, so the loop experiences a decreasing magnetic flux. Then the magnetic field produced by a current try to increase the decreasing magnetic flux. This is how it increases. If the direction of magnetic fields are along the same direction, it increases. If a direction of magnetic fields are opposite, it decreases. If a direction of magnetic fields are along the same directions, it increases the decreasing magnetic. It increases. If the direction of magnetic field is opposite, then this decreases. So loop, you may confuse, right? If I say increasing, right? Loop experiences the increasing magnetic flux. Then the magnetic field produced by induced current try to decrease the increasing magnetic flux. And this loop experiences a decreasing magnetic flux. And the current, the magnetic field produced by current tries to increase the decreasing magnetic flux. So this is the point. I hope now. Yes, this is one more point. You try this. Alright. I'm not going to do this. You try this. Now, what I would like to do is, this is consistent with law of conservation of energies. What I would like to do is, this is very much consistent with law of conservation of energies. So how I'm going to explain this? When I talk about law of conservation of energy, that means law of conservation of energy says that whenever you do some work, then there will be a energy stored. Right? Energy come out of nowhere means that is inconsistent with law of conservation of energy. Right? Energy has to be from some source, that is work. Right? So look at here. I would like to do is, let's say this is a coil. This is a coil. Let's say I have a magnet like this, north, south, and this I push this. Let's say that I just say instead of Lenz's law, I just say it is along direction, right? I just do the converse part, right? So that means let's say that direction of current is going to be this like this, and then magnetic field is going to be along this. This is induced magnetic fields, and this is magnetic field. Let's say if I take a converse of Lenz's law, and then we found that it is inconsistent with law of conservation of energies. If a converse of Lenz's law is inconsistent with the law of conservation of energy, then Lenz's law has to be consistent with law of conservation of energy. This is how I proved, converse proof, right? So this is the point, right? If this is so, current has to be in these directions. Current has to be in these directions. If currents are in these directions, what about this, right? This is going to be a south pole. This is south, right? Now this is south face of coil, and this is a north face, so there will be attractions. There will be attractions. If it is attractions, now if I push little, if I push this magnet, just push it. If I just push it, immediately there will be a south pole and there will be attractions. So I don't really do, and this will go on and on. That means there will be attractions without doing any work. So that means you don't see any work that is doing on our magnets. However, there will be electrical energies, right? I just say electrical energies, electrical energies, right? Electrical energies are produced, all right, without doing any work. Why? Because this is moving on and on. All right, this is moving on and on. All right. If I just take the converse of a Lenz's law, all right. If I just take the converse of Lenz's law, instead of north, it is going to be a south. So there will be attractions. All right. If there is an attractions, so without doing any work, the magnet will come closer and closer to a coil, and there will be an electrical energy produced. And what is the source of electrical energy produced, right? So electrical energies are being produced without doing any work, which is absurd, right? Which is not true. Right? So therefore, this is not consistent with law of conservation of energy, right? And now, what is consistent with law of conservation of energy? The Lenz's law is consistent with law of conservation of energy. Why? Because now I say this is wrong. This is wrong. This has to be like this. If this has to be like this, this is going to be a north. This is going to be a wrong. This has to be a north, right? If this is north, then there will be a repulsions. Instead of attraction, there will be a repulsions. If there is a repulsions, alright, if you don't push, it doesn't move. If you don't push, it doesn't move. It is something like a spring. If you just stretch the springs, unless you push the springs, the spring doesn't stretch. Likewise, if I push, only then it moves. It moves with some constant velocity, right? So if I go on pushings, then there will be an electrical energy produced, and that electrical energy produced comes from pushing. Alright, so mechanical energy is done, that is because of which electrical energy is produced. This is how we prove that Lenz's law is consistent with law of conservation of energy. Thank you.